The masses of the elements shown on the periodic table are weighted average atomic masses. But just what is a weighted average? By the end of this video, you will not only know what a weighted average is, but will also be able to calculate the weighted average atomic mass of elements. We can see 3 isotopes of silicon listed. Remember, the number after the hyphen represents the mass number of that isotope. Take a moment and calculate the average mass of the 3 isotopes. Pause the video while you work and restart the video when you're ready. Most likely you added 28, 29, and 30 and then divided by 3 to find an average mass of 29. Let's compare 29 to the atomic mass shown on the periodic table for silicon. Why is the mass on the periodic table very close to 28, not 29, as we would predict? It's because a weighted average does not weigh or count each value equally in the average calculation. In nature, different isotopes of silicon will have different relative abundances, meaning some may be abundant or occur frequently, while others may be more rare. The more abundant isotopes will count more in the average calculation, and the less abundant isotopes will be counted less. You may be more familiar with weighted averages than you think. Your quarter average is a weighted average. At this school, all the assignments, tests, and quizzes count for 80% of your quarter average, or they are weighted 80% of the calculation. Your quarter exam grade at the end of the quarter counts for 20% of your quarter average, or is weighted 20% of the calculation. To determine your quarter average, your teacher will multiply your grade for all assignments during the 9 weeks. In this example, it was 85. And multiply by its weight, which is 80%. Only first, we change the percent to decimal form by dividing by 100. Remember, to make a percent, you multiply by 100, so to take it out of percent form, we would divide by 100. Therefore, 80% becomes 0.80. We add to that the quarter exam grade, 93, multiplied by 20%, changed to a decimal by dividing by 100, or 0.20. The weighted average grade comes out to be 86.6. Notice the weighted average does not fall evenly between 85 and 93. It falls much closer to 85 because 85 was weighted much heavier in our calculation. This is really no different from finding weighted average atomic mass of the elements. We will multiply the mass of each isotope times its abundance as a decimal, then add it all together. Notice the formula ends with plus ... This is because elements have varying number of isotopes, and many times you may have 3, 4, or even 5 isotopes to include in your calculation. And it's important to remember that we change the percent to a decimal by dividing by 100 before entering the abundance into the formula. In this example, we can see 4 atoms of argon. 2 of the 4, or 50%, have a mass of 36 AMU. 1 of the 4, or 25%, has a mass of 38 AMU, and 1 out of the 4, or 25%, have a mass of 40 AMUs. This means the isotope with a mass of 36 will be weighted more heavily in the calculation since it has a higher abundance than the other 2. We'll multiply 36 by 50%, changed to a decimal, while both 38 and 40 will be multiplied by 25%, changed to a decimal. Add the results together, and the weighted average is 37.5 AMUs. Notice the weighted average skews towards 36 rather than landing at 38 as it would in a straight average of adding the masses and dividing by 3 isotopes. And that's because we're not counting all isotopes equally. The isotope with a mass of 36 is weighted more heavily in our calculations. Now it's your turn to try a problem on your own. Here you see 3 carbon isotopes and the percent they're found in nature. Calculate their weighted average atomic mass. Pause the video while you work, then start the video up again when you're ready. Let's see how you did. Remember, in a weighted average, we will multiply the masses by their abundances as a decimal. Each of the abundances given in the table are percentages, We can't forget to divide each percent by 100 before adding them to our calculation. 98.9% becomes 0.989, which will be multiplied by 12. 1.1% becomes 0.011, which we will multiply by 13, and 0.01% becomes 0.0001, which we will multiply by 14. Add those values together, and the weighted average atomic mass is 12.0124. Let's compare that to the atomic mass of carbon on the periodic table. In this case, you'll notice they are not identical. That's because the actual abundance of carbon-14 in nature is less than 0.01%, but the table didn't tell us how much less. Using 0.01% in our calculation will cause our answer to be a bit higher than it really is in nature. But rounding both to the hundredths place results in the same value, 12.01 AMU. It takes practice to be successful, so be sure to complete all the additional practice problems from class. Thanks for joining me today, and I will see you soon.